I'd like to introduce Gene. Gene is a friend and colleague of Bill's. He's been a friend and colleague of Bill's for a number of years. He hails from the FDA and is cross-affiliated with the University of Maryland. And he has graciously offered to do a quick introduction for Bill, given his working relationship over the years. So, Gene, I'll pass the torch to you.
All right, let me start then. For those of you, of course, by now certainly know that Bill is an emeritus faculty member at the University of Toronto. His early work in NMR focused on substituent-induced chemical shifts and the utilization of long-range coupling constants to evaluate the transmission of electronic effects in aromatic systems. He had one of the first FT-NMR spectrometers in Canada. It was a Varian XL100. Bill has had a long-standing interest in NMR structural elucidation of natural products and has extensively utilized and developed new NMR methods for structure elucidation. He was a visionary at the time, proposing new strategies to analyze NMR data of small molecules. The traditional approach to the chemical investigation of natural products was to gather chemical and physical data for a compound at hand, and then to search the literature to see whether these characteristics were consistent with a compound of established structure. In the years since then, on a number of occasions when Bill has encountered natural products that would have required inordinately high F1 digital resolution, he's returned to C13 detection methods when sufficient sample was available to sidestep sensitivity problems in that carbon dimension. Some of his notable experiments were flock. It employed a small flock of 3 bird pulses, hence the name, and the X-Corphi pulse sequence that was the forerunner of the proton-detected 2J, 3J HMBC and the H2BC experiments that followed in the years 2000 and 2005, respectively. Let's see, okay. Bill certainly has been one of the true pioneers in the field of NMR, publishing in excess of 300 manuscripts, and 36 of them, at my last counting, which was maybe a few years ago, 36 in the pages of magnetic resonance in chemistry. In 1998, he received the Gerhard Herzberg Award from the Spectroscopy Society of Canada. Over the years, his work has extensively involved colleagues and students in the Caribbean and Mexico, broadening their education by exposing them to modern structural elucidation techniques, with many students visiting and working directly with Bill in Toronto. He's also taught a number of short courses in the Caribbean and Mexico. In 2014, Bill was very aptly selected as the first recipient of the James N. Schullery Award for lifetime contributions to the field of small molecule NMR spectroscopy, sponsored by the late Jim Schullery's family and conferred annually at the SMASH Small Molecule NMR meeting. Finally, from 1993 to 2005, he served as an editor for Magnetic Resonance in Chemistry. Hence, it is quite fitting that this symposium is dedicated to Professor William F. Reynolds for his many years of continuous contributions to the field of small molecule NMR spectroscopy. Now, I first became acquainted with Bill at ENC's way back in the early 1970s, when he was the only exhibitor who had posters concerning the structural elucidation of natural products. Even then, you could see that the meeting was moving over toward proteins and peptides. Later, we began sharing car rentals and sometimes rooms at ENCs and SMASH meetings and other scientific meetings of mutual interest. Bill made a great contribution to the discipline of carbohydrate structural elucidation. Carbohydrates represent very difficult structural challenges because, with the exception of the anomeric, that is the C1 carbons and hydrogens, the remaining hydrogens and carbons have very similar chemical shift. Obviously, as carbohydrates become larger, NMR signals overlap more and more, and this occurs for increasing numbers of both non-anomeric hydrogens and carbons. And certainly it's a very serious problem. With Bill's F2 coupled HSQC experiment, carbon-hydrogen coupling is observed in the F2 dimension, where carbon-13 and proton cross peaks appear as horizontal pairs. These cross-peak pairs permit the orientation of carbohydrate ring hydrogens to be determined. Much more importantly, high-resolution F2 coupled HSQC spectra also furnish the magnitude of proton-proton vicinal couplings. Coupling information is thus obtained for carbon-12 attached hydrogens that are adjacent to a carbon-13 bonded hydrogen, which is detected in an HSQC experiment. This information can be critical for complex saponins due to both considerable proton NMR spectral overlap in the carbohydrate region, roughly 3.4 to 3.9 ppm, and the occurrence of vicinal hydrogens that have nearly identical chemical shifts. The determination of vicinal couplings in both 1D and 2D proton NMR spectra is greatly complicated, due to the resulting strong coupling of these hydrogens. However, in F2 coupled HSQC spectra, proton-proton couplings are determined for subunits of the type 1H, 13C, 12C, 1H, in which the approximate 140 Hertz one bond CH coupling effectively results in weak proton-proton coupling by moving the chemical shift of the C13 attached hydrogen to approximately 70 Hertz away from one or two of the carbon-12 bonded hydrogens. Strongly coupled second-order spectra are thereby transformed into easily interpretable pseudo-first-order spectra. This technique is analogous to the use of C13 satellites in proton NMR to determine the couplings between otherwise magnetically equivalent nuclei that are normally inaccessible in typical proton NMR spectra. And with that, Bill, I think it's time for you to give your talk.
Thanks so much, Gene. Really appreciate it. That's very touching. Thank you so much. So it's my pleasure to introduce Bill Reynolds. I'll be actually doing the slides and Bill will take us through the presentation. Of course, Eugene gave the introduction, so I'll simply start sharing my screen so that we can start with Bill's presentation.
First of all, I want to thank everybody, all the kind remarks I've been hearing. It always makes one feel good. Now, to set the stage for what started in 1980, I'll go back earlier, and this has already been alluded to by Thomas Williamson and Jean Mazzola. I was doing a lot of work on electronic transmission effects in aromatic compounds, looking at both proton chemical shifts, coupling constants, and doing initially CNDO type calculations and later SDO3G, the primitive ab initio calculations. I'll just mention one thing that I did, which shows probably why I wanted to change fields. I actually managed to measure a 9-bond proton-proton coupling and determined its sign. The magnitude was 0.11 Hertz. Nobody, I think, since then has measured one any longer, and I can't imagine why anybody would want to either, but it showed the sort of things you could do sometimes with, that was with an HA100. There were some advantages to the old spectrometers in terms of very fine work because of the resolution you could get. Okay, so come 1980, I'd had enough of doing that kind of work. I was looking for something totally different. Oh, you can still go back, sorry. And we were about to get a new 200 megahertz spectrometer, which had all the then available software for 2D NMR, which wasn't very much at that stage. And looking for something new to do, it occurred to me that an interesting project would be to see how useful the 2D NMR would be for small molecule structure elucidation. I decided that natural products were a logical target because of their complexity, spectral complexity and diversity. And fortunately, I knew a possible source of natural products. Now we can go to the next slide. Raul Enriquez, who had family in Toronto, had visited my lab, I think in 1978, and had talked about the possibility of doing a collaboration. And 1980, he invited me down to Mexico City to give some talks at UNAM, the National University. And while I was there, we discussed a possible collaboration. What we decided we'd do is that initially Raul and then later some of his students would come to Toronto with some of the natural products they'd been isolating from Mexican medicinal plants and try out the new 2D NMR methods to see how useful they were for structural elucidation. Now, shortly after that, I discovered there was another possible source of natural products, as shown on the next slide. And that was my colleague, Stuart McLean, who had a natural products background, had received a grant from the Canadian International Development Agency to set up a natural product research center at the University of Guyana. And he'd hired a young Jamaican chemist, Helen Jacobs, to run the facility. His idea was, they had probably a little more primitive facilities, but the idea was they could at least partially and maybe sometimes totally isolate natural products from Guyana, an area that had been very little investigated by phytochemistry before. And then they would bring them to Toronto for often final purification, and then applying as many techniques as they had available to them to elucidate their structures. And once we discovered our common interest, we decided it was logical we should collaborate together on this project. And that's on the next slide. And so what we found, we had these similar goals. We both wanted to bring students up to work on natural product structure elucidation with samples from their home countries. And we decided we might as well collaborate. Stuart would get the advantage of access to whatever I developed with 2D methods, and I would have a greatly increased source of natural products and probably a more diverse source. So I want to comment a little bit about this idea on the next slide. So our goal, our initial idea was we'd involve the scientists and students from these source countries at all stages of their natural product structure research. And the goal of it was that we hope they develop the expertise and experience that eventually they wouldn't need us anymore. They could carry out the research on their own and we could become redundant and then we could afford to retire probably. So now I must say that that wasn't always the way natural product structure elucidation was done in those days. It often happened that a group from a first world country would travel to a developing country, often the tropics, harvest some plant or marine material, bring it back home and investigate it with very little input from the source country. Now, increasingly that was realized that that was unfair, particularly if something valuable came out of the research, like a patentable compound. So in 1993, the International Convention on Biological Diversity ruled that any natural products research must include significant involvement of individuals from the source country. So we were 13 years ahead of our time in what we proposed to do. Okay, by about 1982, I had the spectrometer working. Rowland had arrived with, I think, the first set of 3 samples, and we'd started investigating how the different existing sequences could be used. We quickly discovered that there were 2 of them that were by far the most valuable for structural elucidation. They still are today in their different forms. The first was the proton-proton cozy, where you got sequences of coupled protons identified. And the second one was the carbon-13 het core, which established the one bond connections between those hydrogens and their attached carbons. And what you got out of this was, of course, some molecular fragments or part structures involving a series of protonated carbons. What you didn't get was a complete structure, because typically these would be separated from each other by either one or more non-protonated carbons, or maybe a heteroatom such as oxygen or nitrogen. So you had as I say, bits and pieces. It was a bit like a jigsaw puzzle. You want to know how to put the puzzle together. And how would you do this? Well, I started thinking about this back in 1982. And eventually I had an idea that's shown on the next slide. And that was, why not just re-optimize het core instead of using the one bond coupling, delays for the one bond coupling, which are around 125 to 175 hertz, use much longer delays, which are optimum for couplings in the 2 to 10 hertz range. And the idea was that you would see connections by the 2 and 3 bond couplings to, for example, in this case, a ketone carbon. And what that will allow you to determine was that the 2 fragments on either side, we have a full fragment, an incomplete fragment on the right, would both show connections to the carbonyl, which would tell you that those 2 fragments were attached to the carbonyl group. And so in principle, you could apply that through the whole molecule. If you had, for example, if you had a heteroatom in place of the ketone functionality, then you could see a 3 bond coupling from the hydrogen on one side of the oxygen, in this case, over to the carbon on the other side, and vice versa. So you could also then determine there was an oxygen or nitrogen bridge, probably with the help of the chemical shifts of the attached carbons. So together you could, in principle, put that together as a complete structure that way. That was the idea. And what I liked, the name I liked to give those was INCH, for indirect carbon-hydrogen correlations. I thought it was an appropriate name, a bit like in the inchworm crawling its way along a leaf to put the correlations travel their way along the structure to complete it. There was a couple points about that. They're important, however, that gives you no stereochemical information. That just gives you the skeletal structure of the molecule. To get the stereochemical information, you have to rely on something else like nosy type information or vicinal proton-proton couplings. And of course, for a long time, that was the biggest drawback in structure elucidation, was the stereochemistry. It's only very recently, as talks like what Thomas Williamson covered, that they got some really powerful ways of determining stereochemistry. But nevertheless, we had some primitive methods then. There was another more subtle aspect of this that I think wasn't always recognized for a long time. And that's, as shown on the left side, you've got the 2 and 3 bond couplings, but you can't tell which is which. And that remains a problem to the present day in interpreting now HMPC. You can't always tell which is which. Now, I had this idea, and I talked to it with a few people and got negative responses. They, oh, long delays, lots of relaxation time, signal loss. How do you optimize for delays when you got 2 to 10 hertz coupling? So discouraged me for a short while. And eventually I said, well, I got no other possibility, so why not try it anyhow? And it worked. So one thing I learned from that is never let anybody else talk you out of trying to do something you think might work. Try it for yourself. Unless, of course, they tell you you're going to burn out the probe in the process. So went ahead and managed to elucidate the structures of initially 3 compounds and decided to write one of them up for publication initially, plus present a poster at the NC. Then we discovered, as shown on the next slide, that we weren't the only ones that thought of this idea, which is not surprising. It's sort of an obvious idea. Probably there were 4 papers in 1984. Probably the first was, I think, in actual date, was the one by Klaus Hellenga and co-workers. But probably the most important one was by Horst Kessler and co-workers, because he not only elucidated structure, in that case a polypeptide, but he developed a whole new pulse sequence specific for this experiment, where the rest were using re-optimized het core instead. So, and he introduced the name COLOC for correlation by long-range coupling. So in terms of semantic argument, that seems to win out. And so it's long-range couplings rather than inch experiments is how they're now referred. Now, we hadn't been the first to do the experiment, but for whatever reason, either Collab or Belial's group seemed to follow up too much on this, and Kessler did to a limited extent on some polypeptide work. But on the other hand, by then the samples were coming in from Guyana as well, and we just plowed ahead full speed and did a lot of work on the area. So I think we more or less established ourselves as the first one to use this seriously in the natural product area. I'll go on to the next slide then. Now, in the 3 years from then, as I said, we had already a nice set of samples. We published 9 papers using this method for structure elucidation and NMR assignments, covering 18 natural products. Probably the key one was this compound guanin, where you can tell where it came from the name, which had a really bizarre structure. I deduced it because I knew no natural products chemistry. I just let the data lead me to that structure, and it seemed to go that one and nothing else. I showed it to my natural products colleague, Stuart. He was initially concerned because it was so unusual, until he discovered there was a biosynthetic pathway he could use to explain its formation. So he agreed, and we decided to publish. Now, that to me is the first case of a totally unique structure that was totally determined by NMR methods other than a mass spec to get the formula. So I think that really established the field, and natural products chemists started paying attention. One of the first was Gary Martin, who started using this idea in his days at University of Houston. However, that's not the only thing we were working on then. It's on the next slide. We were also working on pulse sequence development. We actually published 9 new pulse sequences. A lot of them were closely related in that period. Thomas Williamson actually illustrated a couple of them. 2 of them were these ones for determining long-range couplings. XCore-FE was a modified version of COLOC with incorporating 2 bird pulses. FLOC was a modified version of het-core, including 3 bird pulses, which has been mentioned. That's where the name came from. The one reason for them was that the bird pulses helped to produce more correlations. The other sequences had some features that allowed them to miss some key correlations, whereas with the bird pulses in there, we got more correlations. The other key thing was both of those, since the birds are selective decoupling pulses, allowed us to partially at least distinguish between 2-bond and 3-bond connectivities for the first time. Now, that was not complete. We couldn't do non-protonated carbons, and that remains a problem till the present day. But I think we were the first really to highlight this as a problem. So I think by then we'd established the basic procedures for using 2D NMR and structure elucidation. But there was still one very major problem. It's shown on the next slide. And that was that we were using het-core type sequences, and they were very low sensitivity. And what I found, even though we by then had a 400 megahertz spectrometer more sensitive, took at very least 10 to 20 milligrams of sample and a weekend run, and sometimes took longer. So that's not really very practical in many cases, natural products, because you just may not have that much sample. Fortunately, the solution came along thanks to ADVACS in 1986, where developing the 1H detected sequences, where HMQC and HMBC, which are analogous to het-core and COLOC, essentially, except being proton detected. And that gave about something close to a 10-fold increase in sensitivity and the corresponding decrease in sample requirements. So then it became feasible to work on a much more wide variety of samples. Since then, there's been a lot more improvements, as well, as shown on the next slide, in a number of areas, which I've shown here, including, of course, higher fields. The biggest improvements were in the probe development area, probably initially with microprobes, where they use smaller diameter tubes, and the coils were much closer to the tubes, so you got higher sensitivity for the same amount of sample. And of course, cryoprobes, where you cool the preamps and coils and drop the noise level and improve the signal noise that way. The logical extension of that was to have micro cryo probes. I think Gary Martin, more than anybody else, had really pushed the manufacturers to produce probes that would allow them to work with smaller and smaller molecules, which is what amounts of molecules, which is what he needed in his work in the pharmaceutical industry. And he's sort of been the leader in the field. And from what he's written and what he's told me, you could now do complete structural elucidation, maybe as long as he can get by with the standard methods like HMBC is almost difficult, in about 10 to 20 micrograms instead. If you have to use one of his 1,1 adequate or 1N adequate or proton nitrogen, he probably would take longer or require more. Of course, not everybody has that super probe that he uses, but in any case, with all the other improvements, you're certainly in the range to be able to work with milligram amount of samples, even with a room temperature probe. So the whole field has really developed, and we got a chance to take advantage of these improvements in our subsequent research. And we continue this all the way up to about 2016, shown in the next slide. Now, Stewart dropped out, I think around 2005, he was retired and had some health problems, I believe, at the time. And soon before that, unfortunately, the funding had run out for the Guyana project, and essentially partly because of some political interference in their political system by outside countries, the economy was in a mess and they really couldn't afford to run the facility themselves. So, but we managed to replace them by collaborations with the 3 West Indies campuses, which provided an even broader source of samples and students. Now, what shows across the top are the symbols corresponding to the flags of 7 countries from which we had student visits to Toronto as part of this project. It's Mexico, Guyana, Venezuela, Ecuador, Barbados, Jamaica, and Trinidad and Tobago. There was 1 student visit from each of Venezuela and Ecuador, and a number from the others. About 40 students, I would estimate, in total came to Toronto. But overall, we had 212 publications in this area involving about 125 science students. And since not all they could come to Toronto, I also spent a lot of time in the Caribbean and Mexico teaching NMR short courses for the benefit of people in the various areas there. About, I think, 4 in the West Indies and 3 in Mexico. And many of the former students from the province have obtained academic positions since then. And a lot of them are still doing natural products research. And also in terms of NMR facilities, at least 7 I'm aware of were developed with the help of people that have been involved in the project. 4 of them in different locations in Mexico, and 1 each in the West Indies campuses. It wasn't always a new facility. Sometimes they were replacing old facilities, but certainly there was upgrade across the board. So I think with all of that, I can conclude that we had satisfied the original goal of our project, other than the unfortunate fact that the Guyana part couldn't continue. So I think, as I say, I think that part I would regard as a success. We'd achieved the goals. Now, to go on the second part of the talk, next slide. Oh, sorry, I forgot to mention those. Here are the faces of the academic and staff that were involved in the process. I'll mention 2 in particular. Helen Jacobs was the first director of the Guyana Institute. She then went back to Jamaica, where she later became the first female full professor of chemistry in the UWI system, I believe. Winston Tinto was the second director, and he then, when it was closing down, he moved to Barbados, where he is a full professor of chemistry. And then the next slide shows some of the students involved that were involved. Next, yeah. There were so many I couldn't show all of them, or it wasn't even worth trying to put 125 names on a slide. So I instead picked out some of the ones that have made key contributions at various stages. And Darcy had the clever idea, why not put us the structure they worked on, or one of the structures they worked on, along with their names to indicate the sort of complexity of problems they were working on. Of the ones up there, Ramesh and Russell are now faculty members at the UWI Trinidad. Genevieve Henry is a professor and head of the department at Susquehanna College in Pennsylvania. Andrew Marr, who's probably maybe partly hidden, by at least on my screen, is now a director of Natural Products Research Institute and a vice dean at the University of Technology, a new university in Kingston, Jamaica. Frank Ramdayal worked on Guyanan amongst several other compounds, and he was certainly the most productive of all from Guyana. He's now a professor at Bergen College in Connecticut. Sonia Peter is back in Barbados. She's working on a very interesting project as part of general bioculture activities. She's working on the documenting the medicinal plants that slaves in the time of slavery in Barbados used for self-medicating for illness and disease. So that's an important, back to the history, bad history of the country. Lara Escobar, who was actually the first visitor, and that was the first combo we established, is now a professor of physiology in UNAM and in the faculty of medicine. Ismael Leon is a faculty member at the University of Morelos in Cuernavaca, Mexico. Okay, on the next slide, I'll mention only one Canadian student, because she made such an important contribution at the early stages. She was involved for MSc and PhD right through that period. And she was involved in all of the pulse sequences we developed, plus structural elucidation for natural products. She went on to graduate from medical school. Now she's a very successful psychiatrist in Calgary. Okay, now I can go on to the next topic. Now, in the early 1990s, I'd become an editor of magnetic-resonance chemistry. I was starting to handle natural product structure papers in that case. I was also being a referee for a lot of natural products journals. In particular, in the latter case, I was getting quite appalled by the quality of some of the spectra I was seeing. If they showed them at all, I often had to ask to see the spectra to help and judge. And they were sometimes a pretty shocking quality, not always, but sometimes. I thought it was a poor choice of acquisition parameters, trying to get data too fast. And this created a lot of problems in my mind in refereeing. Sometimes the things were so bad I would just reject, but very often I'd look at it and say, well, the structure looks reasonable. I can't see anything wrong with it. I'm not totally confident that it's right either. So often in that case, I had no real strong reason to reject it. I would accept it, maybe suggest some changes. Now, but partly as a result of that, I started a series of writing a series of articles designed to educate natural products chemists how to use NMR more effectively, starting with some specific areas where I thought improvements can be used. But after I started that, sometime later, this very famous paper appeared by Casey Nicolau about chasing molecules that were never there, outlining a large number of cases where there'd been a wrong structure reported in the literature. A lot of that was from early days when you didn't have very good methods for it, but others involved quite modern NMR methods, for example, still got it wrong. Now that started creating quite an uproar amongst the natural products community in general. And next slide, please. Since then, there's been a whole series of articles pointing out even more errors. It's getting to be sort of alarming to read the number of people found. This is very good. This is one of the examples, a very good review by Julia Kubanek and co-workers on how different structure errors were made and how they were detected. Then there's this recent paper by Guido Pauli as lead author, plus I think about half the natural products community in the world involved as co-authors. And they also point out a number of case errors, but they made the argument, which I think is a very good one, that authors for this type of paper should be required to provide the editors with their complete raw NMR data, not just pictures of spectra or tables of data, but the original data. That way, either at the review stage or later, people could check to see if it was right. Now, I don't think that's really practical often at the review stage, because these days, the moment you get a paper to referee, you get another email the next day saying, "Where's your report?" We like fast turnarounds. So I think they rarely be time to catch errors at that stage pre-publication, although maybe having the raw data, you might be able to detect cases where the data were so bad that the structures were unsure, and therefore you could reject on that basis. But it'll certainly help in detecting the errors at the later stages. Now, I think this is a very good idea. I fully support it, but I have a different idea of what I would like to do. Rather than look for other people's errors, I would prefer to try and prevent them from making errors in the first place. As I mentioned, I'd already started on that before the 2005 paper appeared, but I've continued that since. It's one of my second major thrust of my research. And then next slide. Oh, well, yes, that's right. Want to point out that you might say, well, does choice of acquisition parameters really matter that much? And the answer is sometimes it can be pretty important. And we illustrate that in 2009, we'd set out to determine the optimum parameters for acquiring and processing HMBC. We chose that because HMBC is the least sensitive of standard experiments. Therefore, you might have most to gain by finding better parameter choices. We looked at all the possibles, acquisition, processing, etc. And we wanted something to compare with of what was sort of routinely used. And to do that, we chose the information from this well-known book by Berger and Braun, which essentially gave recipes for just about any NMR experiment you could want to run. And we used their parameters, which looked like to me like fairly typical the default parameters where people were using, and ran the strychnine HMBC under the same total time, and found a 7-to-1 signal noise advantage over the optimizer, over the default. Now, I think that's an extreme example. I don't think you'll usually get that much. It turned out there were, I'll mention two of the key parameters. They used far too little F2 data point resolution, which turns out to be very important in HMBC, something I think hadn't been very much recognized. They had far too long a relaxation delay. And so that combination, I think, made a lot of the differences. Now, as I say, we proceeded to publish a whole number of papers in this area, starting on the next slide. I'll only pick out, we had 16 in total, I think, at least. I'll only highlight about 7 of them. The others are quite similar in nature. The very first one was about 1997, when nobody was using linear prediction. Non-uniform sampling hardly existed in the small molecule field, although people in proteins were probably using already. And this was an effort to convince people that they could save time and either save time or get better quality data in the same time by using linear prediction. And I think it had quite a bit of impact, particularly on Agilent variant users where their program built it in almost as a default. Now, Frank will probably disagree, but I think there's still, for routine non-expert users, there's still some advantages to linear prediction over non-uniform sampling because of ease of use and setup. Now, the second one was, I guess, the first of what I would call a recommended best use paper that looked at, with the information we had available at the time, how to make choices about just about everything in structure elucidation and natural products, how to choose which between alternate pulse sequence variants, acquisition parameters, particularly how processing, etc. And that covered essentially all the topics with all the knowledge we had at the time. The third was the one I've already mentioned about optimizing HMBC. And the next slide shows For the more recent ones, these are all fairly lengthy reviews. They were all ones I was asked to write. I keep trying to retire, and then somebody says, could you write this review for me, or could you write this book? And I say, okay, I guess I'll keep going a little longer. The first one was, again, sort of a more general coverage of how to do things in the field. The next was a book we were asked to write, and that's specifically written for non-expert users in the natural products field, to try and help them understand how to do things better. And it had in there a chapter that I think is unique in the field, and that had one chapter devoted entirely to how people can go wrong, tricks they could use to avoid traps, etc., that might lead them astray. And so it's sort of a very specific recommendations for avoiding problems. The next one is a very critical area of natural products area, is that because of this 2-bond, 3-bond ambiguity, plus the fact you often get 4-bond or sometimes even longer couplings in both HMBC and COSY, it's usually true that there will be at least 2 and sometimes many structures that actually fit your data. And if you're doing it by hand, the tendency is to the first one you find that fits the data, you say, oh, that's it, and don't bother to look further. Human nature. The computer program, these case programs, will search for all structures that fit them and give you a ranked order of the probability, usually based on comparisons of estimated and observed chemical shifts. And that's, to me, a very critical stage, something that anybody seriously involved in natural product structure elucidation should consider using as a way to avoid errors. Finally, this last massive effort on our part, where I was asked to write what I called a tutorial for a special issue of DNA resonance chemistry, that covers everything we know on how people might avoid errors, the whole philosophy of avoiding errors, complete set of instructions about acquisition parameters. And I would say, I would think that would be highly recommended reading for any young natural products chemists starting out, to hopefully get them oriented the right way in the first place. It certainly contains everything I know on the subject, and I think everything I'll probably know, because I don't think I'm going to be doing too much more in the future. Okay, so the question is, all these efforts, does it really help? And maybe yes or maybe no. It's unfortunately true that a pretty fair proportion of people using NMR, all they want is to be able to have an icon on the computer screen that they can click on, and then the spectrometer will run whatever program they want for them, with whatever default parameters are built into in the program. Obviously, if they take that approach, they won't benefit in any way from anything I've written on the subject. And of course, for some simpler problems, often in the area of synthetic chemistry, it may not matter too much, because they're not putting so much demand on the spectrometer in terms of the information they need. But if somebody in the natural product field does this, then they're a prime candidate to get the wrong structure. And so what do we do about them? I'll come back to that in a minute. Now, fortunately, it's my experience that amongst natural products chemists, and particularly now students in the field, they're really quite eager to learn more and more about NMR. They realize it's important to their research. And I honestly believe that, particularly in North America, the future experts in small molecule structure elucidation will almost entirely come from the natural products field. We already have seen a good example today. Thomas Williamson started as a graduate student with Bill Gerwick doing natural products, and wanted to get deeply involved in NMR as a student, and Bill encouraged him, and we see where that led to today. So I think it's the wave of the future, at least in North America. I'm not quite so sure about Europe. So what can we do about these people that don't want to bother to learn too much? Well, it's been my idea for many years that it should be possible to develop an artificial intelligence program that will not only interpret their data for them, but also optimize all the 2D acquisition parameters with minimal input. there are already lots of things in the AI type of things for determining structures from data. The case programs that I talked about are certainly examples. The Algarve Smart program is another one. There's the stereo fitter program that Roberto Gil and Armando Navarro Vasquez have been working on for converting stereo-specific data to 3D structures, are all examples of AI type work that allow you to determine structures from data, but less in how you would set the acquisition parameters. Now, there's been some development in that area. Brooker has what they call Smart Drive NMR program, which goes some way to achieving this goal. But I think they could go much further. It's my view that with absolute minimum input data, maybe at most a proton data and either a carbon data or the molecular formula for mass spec, you could have an AI program that could pretty well optimize all the key parameters, including the recycle time, and probably do a fairly reasonable job just with the information you could extract from a proton spectrum. And if that were available, the results would be that the people that didn't want to learn wouldn't matter. The spectrometer would be doing the thinking for them, and they could still get the right answers, their best possible results that way. So it would help the problem of people that didn't want to make the effort to really understand NMR. Now, of course, this could be carried to its logical extension, and that with combining that type of program with a case program, the person could input the sample, maybe tell them what experiments it wanted to run, and the spectrometer would run all the experiments, would run the case program, print out at the end a list of possible structures ranked according to probability. From an educational point of view, I don't like the idea at all, but I have a feeling that that's what the future will bring in the field, that it's going to be much more automated. I mean, already the spectrometer manufacturers seem to be doing the best they can to make it as easy as possible to not have to think about what you're doing with NMR. So I'm afraid that is the future. Maybe it's a good time to retire when that happens, because it takes some of the fun out of the game, I think. Okay, to go on to the end. I've been very fortunate. I've been doing NMR actually for 61 years almost now. And what's happened has been absolutely amazing, the way it has evolved. When I started, there were mostly a number of physicists and physical chemists using NMR with pretty primitive equipment and limited range of problems. And now it's evolved to the point where people in many areas of science and medicine are using NMR. They're performing a lot of very sophisticated experiments to extract a lot of information that would otherwise not be available. So it's really been more of a revolution than an evolution. Now, a lot of the improvements in the hardware, including the spectrometers, and to give them higher field, higher sensitivity, and better electronics are important. But to me, the real key was the replacement of continuous wave, which I was using in 1960 for excitation, with pulse excitation, because that led the way to all these sophisticated pulse sequences, which are now used to extract information that would otherwise be very difficult to get. This covers the whole range. My colleague, Toronto Lewis Kay, who's managed, for example, to identify invisible intermediates along the protein folding pathway with some very sophisticated and very clever pulse sequences. To the other end, you've got people in the food industry and manufacturing using 60 megahertz benchtop spectrometers very effectively to help in their businesses. And again, the key to both of them is the ability to use pulse sequences to extract information. So that as a result of this, there's no doubt in my mind that modern NMR started in 1966 with the paper by Richard Ernst and Wes Anderson on pulse Fourier transform NMR. Everything good followed from that, and that's why the loss of Richard Ernst is such a sad occasion. Now, what did I get out of all this? Well, I think in my own efforts in the last 4 years in this specific areas, small molecule structural elucidation, I like to believe I made some significant contribution, particularly at the early age of establishing the methodology. And certainly I probably managed to help determine the structures of something like 250 natural products, which I guess is an achievement. To me, though, the most important part is the educational component, the training that I've been able to give to particularly the students who work with me from Mexico and the Caribbean, but also the broader NMR community that I hope I've helped. And to me, that's the most satisfying part, because that is the one that has lasting impact. And that was the learning, the teaching part of my title, but there was a learning part as well, because I've also had the opportunity to follow and not only understand, but often make use in my own research, all the important advances other people have been making. So this has allowed me to keep learning, keep evolving, and keep my mind from stagnating. So that's, to me, the learning part. There's another part I learned too that's important, is that doing NMR research is a whole lot of fun, which is probably why I managed to keep doing this for so many years. And so when I think back, Thomas Williamson mentioned I'd been doing phase diagrams. I was glad to escape from that. When I think back the day in the summer 1960 that I met with Professor Ted Schaefer and agreed to start doing NMR research with him for my PhD, I made the best possible career choice I could have ever made. Okay, now finally for the last slide. So we've been going on too long. There are a lot of people I want to thank for this. I particularly want to single out Darcy Burns he did a lot of the bull work in the organization and also helped me with my slides. Finally, I should also thank my wife, Chris, for putting up for so many years with somebody that just can't seem to understand the concept of retirement. So for all of you on the screen, especially the people that decided to participate, thank you. And that's all I have to say.